Hey everybody, this is Mike Bartles from the Hydrologic Engineering Center. This lecture is part 3 within a series of lectures that are devoted to parametric modeling from a hydrologic and hydraulic modeling perspective. Within this video, we'll discuss how to select a model and parameterize it using your data. By the end of this lecture, you should be familiar with some commonly used probability distributions within hydrology and hydraulics. You should also be familiar with several fitting methods used to parameterize those probability distributions. Through examples, you'll see how fitting methods can be used to estimate the parameters of various analytical distributions. Let's begin by revisiting the steps needed to perform a parametric modeling exercise or fit an analytical distribution. Within this lecture, we're going to focus on steps 2 and 3. Step 2 is the selection of a distribution and fitting method. When put together, a distribution and a fitting method create a model. Step 3 focuses on computing parameters of the model. Here are some common continuous probability distributions that are utilized within water resources applications. Aside from the familiar exponential, Gumbel, normal, and Pearson type 3 distributions, I'd like to highlight the extreme value distributions noted at the bottom of the list. These distributions are part of the family of 3-parameter distributions for which parameterization schemes were devised by Hosking and Wallace. Each has a location, scale, and shape parameter. First is the generalized extreme values, or GEV, distribution. This distribution subsumes the 3 extreme value distributions, Gumbel, Frichet, and Weibull. Which distribution it represents is dependent upon the shape parameter. For instance, GEV equals Gumbel when the shape parameter is equal to 0. Now, the GEV distribution is commonly used for precipitation frequency studies within the United States and many other applications like flow frequency outside of the US. The GEV distribution was derived by taking the maximum of repeated independent samples from a homogeneous population, which is what is commonly used to create annual maximum series. Next up is the generalized Pareto, or GPA, distribution. An underlying assumption of the GPA distribution is that subsamples exceeding a sufficiently high threshold from repeated samples of a homogeneous population will converge to the GPA distribution. So in other words, if repeated samples are taken from a population and only the values in those samples that are greater than the selected value are retained, then those retained values will follow the GPA distribution. This type of data set is called a partial duration series, which is something that we discussed in the previous lecture. Finally, I'd like to mention the generalized logistic, or GLO, distribution. Like the GEV distribution, the GLO distribution is commonly used in precipitation frequency studies within the United States. Discrete probability distributions are used to describe the expected results from experiments where only a certain number of outcomes can be realized, like flipping a coin or rolling a die. These distributions aren't used as much within water resources applications, but they are still used from time to model things like, will it rain tomorrow? If it is going to rain, what type of storm will it be? And so on and so forth. Continuous probability distributions are used much more commonly within water resources applications. This arises from the fact that we tend to model phenomena that are comprised of continuous random variables like stream flow, precipitation, or stage. Similar to a unit hydrograph, the area under the probability density function, or PDF, must sum to 1. An example of a PDF is shown in the upper right-hand image. Also, the cumulative distribution function, or CDF, must span 0 to 1 and cannot decrease. An example of a CDF is shown in the lower right-hand image. Now let's discuss some fitting methods. As mentioned before, the same analytical distribution can be fit to the same dataset using different fitting methods to obtain different parameterizations and, as such, different quantile estimates. When we fit a distribution, we are using the child population because we don't know the true parent population. In fact, within all real-world applications, we can't know the parent population. We can only know the parent population in contrived examples. Some commonly used fitting methods are the method of moments and maximum likelihood estimation. And some special extensions of the method of moments include linear moments and the expected moments algorithm, or EMA. Greg will go into more detail regarding linear moments and their applications, while Beth will present several videos detailing EMA and its uses. The method of moments fitting method is widely used within water resources applications because it's pretty simple and fairly robust. The underlying assumption of this method is that the parameters of the child population are the same as the parent population. Remember within the last lecture when I stressed how important it was to develop an IID and representative dataset? This assumption is the reason why you should spend a lot of time developing and processing your dataset. Within this method, equal weights are given to the transformations of the observations. As I said before, the method of moments is used within both Bulletin 17b and Bulletin 17c procedures. However, Bulletin 17c makes use of a generalization called EMA that allows for the use of some unique types of data like intervals. Now let's step through an example application. In the upper left image, I have an annual maximum series of streamflow. In the lower left image, this annual maximum series has been transformed to log 10 values. Next, the log parameters of the sample are computed and shown in the blue text. Then, those parameters are used to fit both the log normal and log Pearson type 3 distributions in the orange text. The log normal distribution does not use the skew parameter. Only the log Pearson 3 distribution does this. Notice that the parameters of the sample match the parameters of these two distributions. That's the consequence of assuming that the parameters of the child population are the same as the parameters of the parent population. Finally, the fitted distributions are plotted along with the plotting positions of the data in the right-hand image. Linear, or L moments, are widely used in precipitation frequency studies. They become especially useful when regionalizing parameters. This fitting method is an extension of the method of moments in that it still assumes the parameters of the child population are the same as the parent population. However, unequal weights are given to the order statistics of observations based upon their ranks. In particular, less weight is given to the tails of the distribution. Hosking and Wallace revolutionized the use of this fitting method, along with the three aforementioned distributions, in the mid-1990s. More on this fitting method will be presented within other videos. Here's an example application of L moments. An annual maximum series of flow is used to compute the L moments denoted as L1, L2, L3, and L4. Then, those L moments are used to compute the L moment ratios, L mean, LCV, L skew, and L kurtosis. Using these linear moments, the three-parameter GEV distribution can be parameterized using a scheme put forth by Hosking and Wallace, and is shown along with the data in the right-hand image. Maximum likelihood estimation, or MLE, is a much more complicated fitting method than the previous two methods that I described. As such, this method has not been as widely used in water resources applications, but it is commonly used in other arenas, like the financial and actuarial industries. This fitting method, like EMA, is able to incorporate point, censored, and interval data. However, this fitting method is also able to integrate arbitrarily complex distributions. Other topics related to model fitting include regionalizing data, analyzing ungauged areas, and incorporating historical and/or paleoflood data. Historical and paleoflood data are oftentimes missing direct observations and are best represented by interval or censored observations. These topics will be covered in additional videos. Also, we have another class dedicated to these topics. If you're interested, please check out our flood frequency analysis class for more information. In this video, we talked about the selection of both an analytical distribution and a fitting method. When put together, these two create a model from which we can draw conclusions. We discussed commonly utilized distributions within water resources, as well as several examples of fitting methods. The next lecture, we'll discuss how to visualize a model and verify its appropriateness. Thanks for watching, and I'll see you in the next one.